All right, let's dive into something really cool today. We're going to talk about a pretty wild innovation where researchers are using the basic laws of physics to fix one of the biggest, most stubborn problems we have in modern AI. So you know these incredible transformer models? They power pretty much everything, from ChatGPT to all the crazy image generators. But what if I told you they have a critical hidden weakness, a flaw that, believe it or not, actually gets worse the bigger and more powerful these models get? So, what is it? The problem has a name: over-smoothing. And honestly, it's kind of what it sounds like. Imagine information passing through layer after layer in a deep AI model. As it goes deeper, the unique details of each piece of data, what we call a token, start to, well, they blend together. They lose their sharp edges and all start to look the same. This has been a huge roadblock, limiting just how deep we can build these things. Now, to solve this, a team of researchers decided to think way outside the box. Instead of treating it like a typical software bug, they took a step back and started looking at the entire AI model as if it were a physical system. Something that has to follow the laws of physics. And that's exactly where they had their aha moment. Okay, this slide right here is the absolute heart of the idea. They realized that standard transformers act a lot like diffusion. Like dropping a bit of ink into a glass of water. It just spreads out, fades, and loses all its original shape and detail. The information just dissipates. Their solution? To build a model that acts like a wave. Think about a ripple on a pond. It doesn't just fade away, it travels. It preserves its energy and carries a clear signal from one side to the other. That one simple shift in perspective from diffusion to waves is the entire key. And this isn't just some loose metaphor I'm using. The researchers spell it out right in the paper. The math that underpins a normal transformer is basically the same as a diffusion equation, like how heat spreads through a metal rod. It naturally wants to even everything out, to smooth it all into a uniform state. Understanding this was the key to unlocking the whole problem.
Okay, so the theory is just brilliant, right? But how do you actually build an AI model that follows the physics of a wave? That's the tricky part. To do that, the researchers had to get under the hood and fundamentally rewire its internal mechanics.
They did it in 3 main steps. First, they gave every token a velocity. It's a new piece of data that basically tracks its momentum, how it's changing as it moves from one layer to the next. Second, they ripped out the model's core update rule and swapped it with one based on the actual wave equation from physics. And finally, they had to tweak all the other essential parts, like normalization layers, to make sure the whole system was consistent with this new physics-based approach.
But here's where it gets really clever. The solution wasn't just to throw out the old diffusion method entirely. Nope. The model that performed the best was actually a mix of the two. It has this smart little parameter that lets the model learn when to let information spread out and when to let it travel like a wave. It literally gets the best of both worlds. So that all sounds fantastic on paper, but you know what matters? Does it actually work? Let's look at the proof. Time to put this wavy transformer to the test. First up, language understanding tasks, using the standard GLUE benchmark. The original diffuse model scores a flat 67. The pure wavy one? Pretty similar, actually. But look at that mix model, the one that combines both. It clearly pulls ahead. It's a solid, measurable improvement.
And this isn't just a one-trick pony for text. They tested it on computer vision, and you see the exact same pattern. The standard model gets about 72.2% accuracy. Another method to fight smoothing gets a small bump, but the wavy mix version comes out on top again, pushing the accuracy even higher. And the best part? It does this without adding a bunch of extra complexity or parameters. It's just better.
Better scores are one thing, but remember the whole point of this project? It was to fix that core problem of over-smoothing. So, did the wavy transformer actually do that? Well, the next chart gives us the smoking gun. And there it is. This chart shows us exactly what's happening inside. It measures how similar all the tokens are by the time they reach the final layer. In a standard transformer, that similarity is super high, around 0.8. That's over-smoothing, right there in the data. But in the wavy transformer, that similarity is significantly lower. The tokens are holding on to their unique identities. The wave physics, it's actually working. So let's zoom out for a second. We've got a new model, inspired by physics, that gets better scores and directly fixes a fundamental flaw. What does this all mean for the future of AI? Why is this such a big deal?
Well, it matters for a few huge reasons. First, this is more than just a new model. It's a whole new design philosophy. It proves we can look to the fundamental laws of nature to build better AI. Second, it tackles the over-smoothing problem head-on, which could let us build much deeper, more capable models. Third, it just plain works better.
giving us improved performance without the extra cost. And finally, it really opens the floodgates for more nature-inspired ideas in AI research. It really makes you wonder, doesn't it? If something as fundamental as the physics of a wave can solve a problem this big, what other secrets from the natural world are just sitting there, waiting to unlock the next massive breakthrough in AI? It's a pretty exciting thought to end on. Thanks for joining me for this one.